we are ready to start. Ну, Брюс — это человек, который в России бывает с завидной регулярностью. Между визитами в Россию он, вообще говоря, глава core-тима PostgreSQL. Что это такое, он может, наверное, сам рассказать, вы у него можете спросить. Ну и, соответственно, прошу любить и жаловать, встречать аплодисментами. Мы готовы начинать. Соответственно, probably 1 minute break to divide to rooms, and if someone want to go upstairs, it's time to do that. And then Bruce can start.
Привет. My name is Bruce Momjian. I am here from Pennsylvania. I actually live near Philadelphia, and I'm very happy to be here at your event. I want to apologize for not coming last year. How many of you were here last year at the conference in July? Wow. Okay, a lot of new people. Good. I was not able to come last year, so I'm very happy to be here. Finally, I love Moscow, I love St. Petersburg, I love Russia. This is probably the 7th time I've been to Russia, and I always have a very good time. My wife and daughter have come with me this time. So if you see somebody who looks like me, if they're female, that would be them. And they're here for the entire week. In fact, I'm here until Wednesday to sightsee and to see your wonderful city. This is, I came last in November, I think, and spoke to some of you. Any of you hear me speak in November? Oh, I got more of you. Good. Okay, great. That was a really nice event. This is going to be obviously much longer and a much bigger event. I'm looking forward to it. Magnus, where are you? You're back here somewhere. He's going to be speaking after me, after lunch, so it's going to be a really good day, and I think it's going to be a really good rest of the week for us. So again, my name is Bruce Momjian. I'm one of the Postgres core team members. I've been, sorry about that. I've been working with Postgres for 19 years, so a long time. One of the sort of first people to get Postgres out onto the internet. My website is actually right here, so if you want to find out more, you can go there. This presentation is also at that website, so if you want to look at the slides later, you can do that. I'm going to be showing a couple presentations. I'm sorry about the date, I fixed it, but I guess I didn't upload it to the memory stick is a little older. So this presentation and a whole bunch of others are up on my website, and feel free to look at those. There's probably 20 presentations, 30 presentations on that website. They're all PDFs. So some of them have videos, so if you're curious to actually watch me giving a presentation, that just, if you can barely spell my name, it'll find it usually. Again, thank you for having me. I'm looking forward to it. It's great to see a lot of old friends. We had a nice time last night, sort of catching up with everybody. So what are we going to do today? What are we going to do for the next 3 hours or so? Well, the first positive thing is we have a coffee break in the middle, so we're not going to do 3 hours, right? We're actually going to go until 12 o'clock, and then we have a half-hour coffee break, so some time to get up and relax a little bit, and then when we come back at 12:30, we're going to go until 2 o'clock. So it's kind of like about an hour and a half and a break, and then another hour and a half, and it's kind of nice to break it up that way. I'm excited to be giving this particular content. I don't get a lot of chance to talk about the internals of Postgres. A lot of people want to hear about the features of Postgres, or what's the next, what's going to be the next feature, or how do I use this feature. Not a lot of people really want to understand the internals, especially in a long class like this. And I think it's going to be really nice to be able to give you a full span of everything that happens inside the database. Because frankly, the reason I'm involved with Postgres is because of the internals. When back in the mid-1990s, I was an application programmer. I wrote database applications. And I used commercial databases to do that because at that time, there are not a lot of open source databases. I used Ingress and I used Informix, which were two of the big ones at that time. And as an application programmer, I wrote SQL, and I sent the SQL to the database, and the database somehow figured out what I wanted and gave me the results. And it was kind of magic to me. Like, how does it understand these words that I type and do what I asked it to do? So I've always been curious, how does that thing happen? How do you send these things to the database, and how does the database understand what you want to do? And that's what this presentation is about. It's basically about trying to explain, how does this thing work? Because when you understand how it works, it's very elegant, it's very interesting, and you get a new perspective on the database. So one of the reasons I got involved was just curiosity. How does this thing work? What does it do? What does the optimizer do? How does it know if I should use an index or not? How does it know if I'm missing, if I did a syntax error? How does it know that? These are all kind of details that I was curious about, like how does it do it, and that's what I was able to write down. And some others in the community, particularly Tom Lane, one of the reasons he got involved was also that curiosity. How does the optimizer work? How does this thing do what it does? And of course, I couldn't look inside Informix, I couldn't look inside Ingress, but Postgres I could look inside because I could see the source code, I could see how it worked. And that just always fascinated me, and that's what I'm going to be talking about in this session. So I'm actually going to use a couple different presentations. I'll use this one, but then some other ones as well. And I'm also looking for questions. If you have any questions, we can talk about them during the session, so we don't have to wait to the end because that doesn't work too well. So I think we can take a couple questions at specific spots if somebody wants to know about something. And I also have a, where's my translator? Where did she go? Theodore, where's Ksenia?
Outside.
Outside? My translator has left me, but we'll get her back in if somebody needs help with saying something in Russian and then converting it to English. Yes, you will be glad to help me. So obviously I understand language is difficult. I wish I spoke Russian. I can read the letters, so like I can read the Cyrillic. That's like a big deal for me. That's as far as I got, but it helps. But again, if anybody, I'll try and speak slowly and not use any big words, and that kind of helps. But again, if anybody gets confused or whatever, I'd be glad to make it easier. Does anybody have any questions before we get started? Like anything? Okay, yeah, probably not. So let's get started, and I'm gonna basically walk through an SQL query, and I'm going to show you how that SQL query is processed inside the database. One of the reasons this is called Postgres internals through pictures is because, if I can't see it, if I can't visualize, if I can't see what's happening, I don't understand it very well. If I can look at it and I can actually see the letters and I can see the commands and I can see exactly what it's doing, I understand it better. So this presentation is kind of designed around the idea of showing you visually what's going on. So here's a query right here. And again, we're going to walk through this query for quite a while, kind of showing you how it works. Okay. But the first thing you're going to notice about the query is the colors. And that's kind of an allusion to what we're going to be talking about in a minute. Notice that some of the words are green, some of them are black, and one of them is red. And that idea that even though when we're typing an SQL command, all the letters look the same, right? They're all kind of the same letters, A, B, or whatever Cyrillic you're using, well, although you probably can't type Cyrillic SQL yet. But the words actually, the letters actually have different purposes in the command, and I'm going to help to kind of explain that. And that's kind of a key to understanding how a query is run. So, a very simple query again, up at the top, same query, and we get one row, one value coming out at the end. This person named Sandy, whoever that is. So what we're going to look at is the part in the middle. So we're going to look at the part between when you type the query and when you get the result. We're just going to expand that out. We're going to expand that out. We're going to expand that out and show you exactly what's happening inside of there. Okay. So the first thing that happens when you type an SQL command is that it's basically passed down to the first layer of Postgres, and that is what we call a client library. Okay, in this case, it happens to be a library called libpq, and libpq is a C library that actually acts as an interface between your application and Postgres. How many of you have heard of libpq? Okay, that's good, that's good. So if you're using, you might not have heard of libpq, but you may be using it if you're using Python, if you're using Ruby, if you're using Perl, if you're using embedded C. All those actually use libpq underneath the language to communicate to Postgres. In fact, the two that don't use libpq are JDBC, which is pure Java, that doesn't use libpq. And then ODBC kind of uses it, kind of not. It uses part of it. But again, libpq is an interface library, and so what happens is that in this case, I'm running PSQL. You may recognize PSQL. And it calls a function called pqexec, which is named from the 1980s, I think. And effectively, what it does is it gets a string that comes down from libpq, because you type the string in and then it passes it down to the first layer. That's the interface layer. Okay? And there's my string, and you can see the new lines are actually listed with a \n, because they're like new line characters in C, because again, Postgres is all written in C. Okay? So after it goes to pqexec, oops, sorry about that. After it goes to pqexec, it actually has to go across the network. So here's my application code, and here's my interface library. And remember I said I was going to go further and further down. So I go to my interface library, I send the query over to the database server. The database server is going to execute the query, and then it's going to send the result back to libpq, and then from libpq it goes back up into the application. Okay, so you can kind of see why libpq is like an interface library, because it's the connection between the application and Postgres. So as I said, it has to go across some kind of network. Here is actually a TCP packet, which you can see really slightly the command here at the end. Okay, up here the earlier bytes relate to the TCP header, the checksum, the length of the packet. There's a whole bunch of overhead that is part of the TCP packet, and it's kind of up all in this jumble here. But you can see the letter Q, which represents a query, means a query's coming, a special letter, and then we have a select command, and that's going across the wire. The new lines are still in the command. So let's see here. Here's a new line right here, and here's a new line right here. You can see the OA, which would be the hex characters for new lines. So it's basically just taking that string that I typed in PSQL and sending it to libpq. libpq is going down to the network, okay? And then it's arriving at the server. Here is a set of server logs, and you can actually see the name of the binary, and actually here is the query arriving at the server. All this stuff before here was all happening in the client. Okay? Now we have it arriving at the server, the query is getting processed, and then we're returning a result, and then it's exiting. So it's a very, very straightforward setup so far. Okay. Are there any questions? Anybody like to ask a question? Okay. Yes, sir.
What does PQ stand for?
Yeah, that's a great question. What does PQ stand for? It always kind of confused me, and it confuses a lot of other people. The reason it's called PQ is something I talked about earlier. I said the name libpq goes back to the 1980s. So when Postgres was originally developed, SQL was not the dominant language that it is today. There were actually two relational languages in the 1980s. One was SQL, which was sort of championed by IBM. And then there was another language called Quell. It's Q-U-E-L. And I actually used Quell in the 1990s on Ingress. So there were actually two relational languages in the 1980s. And Postgres originally was written to use Quell, the other language. And only in 1995 was SQL added to Postgres. So it's called libpq because it's libpostquell. And we've kept the name because we use the same API, pqexec. It's called pqexec because it's postquellexec. I don't think we would have named it that way today. But because that's the way it came to us from the university in California, we've just kept the internal names and the library names the same. And it is, yeah, we very often get that question. Why is it PQ? Like what? So originally it was postquell, and that's what it was designed to do. Very interesting. Other questions? Oh, good. Okay, good. Yeah, that postquell thing always gets people like, why is this Q there? It's just very odd. So the query arrives at the server. Ooh, yeah. This is really gruesome. I don't expect anyone to understand it. But what it's showing you is that this command that arrives, there's a lot of work. A lot of work happens inside the server. So This command arrives at the server, and all of these things have to be created and processed and executed before we can return a result. So I'm putting the slide up here just so you can understand there's so much going on. When you type a single SQL command, there is a huge amount of work that happens. And we're actually going to walk through this. By the time we're done, this will make more sense to you than it does now. So I promise it'll make more sense, I think. So let's break apart the first piece of this. Okay. What I've done is I've taken this incredibly long thing that really you can't understand, and I've done what we call a printed it kind of structure, a little more structured. Okay. And what you can see now, it starts to look a little like JSON, doesn't it? Where you've got sort of a key and a value and a key and a value. It's not JSON, but it looks kind of like that. And we have a hierarchy. We have an indenting. We have we can have a key, a value. Then we can also have a key that has a structure underneath it with more keys and more values. And that's what that is, except it's just written out like this. Okay? But internally, it's a very powerful structure that is kind of, and we're going to talk about this in a couple of minutes, but I just wanted to kind of explain. It doesn't actually look that bad. If you print it, you can kind of see there's some logic to what's going on here. Okay? And this is kind of the slide I wanted to kind of talk about in a little more detail to kind of help explain this big jumble here. Okay? The query, when it arrives on the server, goes through some very well-defined stages. So every query that gets executed has to run through a predefined number of stages to generate a result. And these stages are not specific to Postgres. So pretty much any of the relational databases are going to use a similar type of system to run a query. So I'm going to talk about Postgres here, but if we were to look at Oracle, or we were to look at the DB2 or Microsoft, they're going to go through very similar stages inside their databases, pretty much the same as Postgres. Okay? So the three stages generally are what we call the parsing, which I'm going to go through in detail. Okay? And then the optimizer, which you've probably all heard about, but maybe weren't sure what it did. We're going to go to that in detail. And then the executor, and that's really where all the action happens. That's sort of the final stage where we actually run the query and we generate the result. Okay? So, again, when the query comes in, the first stop is the parser. Then there's a rewriter at this point. The optimizer is down here, and then the executor. And this is a blow up of that slide, so you can kind of see, I think, the stages pretty clearly. When a query comes in, we have to find out what query is it. What is it? Is it select? Is it an update? Is it vacuum? Is it alter table? Like, we have no idea. All we see when a query comes in is a string. Right? All we get is a string. But we have to interpret that string, and we have to identify what type of command is this. And if the command is a select, an insert, an update, or delete, we then go down and we go to the rewriter and the optimizer and the executor. But if it's not one of those, if it's a create index, we actually have a separate section called utility commands. And we just go over and we say, oh, that's not like a standard command. That doesn't need the optimizer. That doesn't need the executor. They just want to show a variable. They just want to create an index, or they just want to alter a permission with grant. So those are all handled specially in a different area. So I'm not going to talk about those too much. I'm going to talk primarily about the insert, update, delete, and select cases. Okay, because those are, I think, the most interesting, if that makes a lot of sense. Okay. Any questions so far? Okay.
What about procedures? Sometimes inside procedures as queries.
Yes. So that's a great question. So the question is, what happens when somebody executes a function and the function, this is a really good question.
Maybe function in select
Right,
fields.
right. This is a great question. So, and I'll always try to repeat the question so everyone can hear what the question was. And thank you for your English. That's obviously very helpful, considering my translator has disappeared. But I'm giving Theodore a hard time. She's out having fun with my daughter. Yeah, and my wife, yes. So the question is, what I've shown you, this is a very good point. I've shown you all these examples of libpq getting a query from an application, right? Well, let's back up. Let's back up and really understand what this person is asking. So they're saying, I understand when you run a query and you send it across the network, that you run a query and it goes into libpq on the application, on the client, and then it goes across the network and it arrives and it gets executed, come back. But he says, what happens if I call a function and that function issues a select statement or an update statement? You see what the person's saying? Queries don't always have to come from the application. They could come from a function or a trigger, okay? And that confused me too initially when I started. But what happens is there's a special server-side library called SPI, Server Programming Interface, SPI. And SPI is a C interface for calling SQL on the server side. Okay? So it doesn't use libpq, it actually bypasses libpq and starts another, it kind of
instance of backend inside.
It's got it's like a new version of the back end that runs inside of itself. So if you're running through a function and it does a select, that's going to go out and go through this entire stage again, give you a result, come back, and then keep going through the function, and then there's an update or delete. It's going to go out, it's going to go through the thing again, and it's going to pop back. So it's kind of like a new version of Postgres that's running while the function is running. Very interesting how it works because, again, it's not a client, it's not running on the client, it's running on the server. The Postgres manual has a special section called SPI, or Server Programming Interface, and it talks about how to use that in your app, in function code, because you can write, if you write your functions in C, your server-side functions in C, you still want to be able to call SQL functions, and it gives you the API that you would use in C to do that. Okay, and that's usually that's the way you do it inside. That's a great, because I was trying to make it really simple, but that's another really useful point, that you can call the application within inside the inside of the thing. So good. Yes, sir.
It works in the same process, or it spawns another one?
So the question is, the question is, does it use the, is it running inside the same process, or does it spawn a new process? It's actually running inside the same process. if we were to have to create a new process to run an SQL, it would be very expensive because we don't, it's not a threaded backend, so you'd have to create a whole new session, a whole new process, and start it up and connect and authenticate it, and then it's just way too expensive. So it's actually running inside, and it's pretty tricky because imagine, I mean, let me give you a very interesting example. When you create triggers, those triggers are going to run at the end of your insert or the end of your delete. You know, you create an insert trigger. So you do an insert, right? And then we're going to call the trigger, and the trigger itself might do another insert or another select or something, right? And then you're actually in the middle of a command and you're running another command, another whole process, a whole flow of activity inside of it. You know, I'm not, Theodore, can you talk a little bit about how does that work? Like, is the insert finished at that point and then you run the triggers? Is that how it works pretty much? So you've run your whole select, you've run your whole insert, and then we run the triggers at the end, I think is how it works, right? Right, so technically the command is over, we've gotten to the bottom, and then we run the triggers, and the triggers are going to call SQL functions, but we've kind of finished at that point. We've got all the triggers in a portal, and then we just run over them. We run over them, and we're not technically running an insert inside of an insert as bad as you might think, right? Because if you call a function, well, that function's just a select, and it just runs whatever you want, and it doesn't interfere with what else is going on. Yes, sir?
Is there any specification for parsed query format, abstract syntax tree, or it's only inside sources?
So is there any specification for the parse tree and how you would understand that, or is that kind of embedded into the code itself? It's actually embedded into the code. I'm going to show you the parser. So the parser is written in a language called Lex, or actually Yak, or Bison, and I'll show you that language. But there's no real like external API for that. You can't like put a new. We've had people ask a lot. They want to put a new parser into Postgres.
Yeah.
And just plug in
New languages.
new languages, right? Like let's take select, right? And let's make it Cyrillic, and we'll just like allow people to type Cyrillic Russian SQL, right? Why not, right? It would make sense.
PostgreSQL.
Yeah, right. Yeah, but there's a whole bunch of uses we could make of that. But when you start to look a little farther, you're going to see it's really hairy to do because the actions are tied directly to the grammar, and it would be really hard to abstract that out and not like break everything. So we talked about it. So it's a good question. How would you abstract out the parser and put a new one in, make it look like MySQL or whatever? We talked about it, but we've never really figured out how to do it in an efficient way. Yeah. Other questions? Oh, very good questions. Great. So, speaking of actually parsing, let's walk through how the parsing works. Okay. How many of you have dealt with parsing before in college or? Wow. Okay. Oh, a couple. Good. Okay. I hadn't. I actually have no computer education experience at all, so I have not dealt with this. I read all the books. So I actually, when I went to college, I majored in history. So that was my thing, and I also majored in mathematics, which helped a lot. But I never had any formal computer science training. So when I got into Postgres, I was like, well, I'm curious, how does this parsing thing work? And I read a couple books, big thick, 500-page parsing books. And grammar. But it was really, I learned a lot. That's how I taught myself. Same thing with operating system design. I read a whole bunch of the big books about that, and I played with it. I tried it, and I was like, that's pretty cool. So let's try and explain how this works. And this kind of gets back to our original query. Do you remember our original query way back? And I mentioned that the colors are different, okay? Some of the words are in green and some of them are black and one of them's in red. And that's actually because of parsing. There is what we call a scanner. It's actually a lexer. I know that's, for those of you who are like computer science majors, there's actually two things you do in the parser. And one of them is lexing and one of them is parsing. So technically, I don't know how it is in Russian, but I know in English they're different things, and I assume it's the same here. So effectively, what you do when remember we sent that string, we sent this very long string here, right, to the server. And what happens when that string arrives is that it goes into the scanner. And the scanner basically takes that long string and it breaks it up into tokens. At least that's the English word for it, called token. And a token is basically a set of words or symbols, usually separated by white space of some type. It doesn't have to be, but for SQL, normally they're separated by white space, although a string, an SQL string, is separated by single quotes, right? That would be a whole token. Even if it has spaces in between it, it starts with a single quote and ends with a single quote, right? That's how you identify a string. What I've got up here is a scanner definition for an identifier. Identifiers have a particular name, have a particular purpose in SQL, as it does in most programming languages. And in SQL, a token, an identifier, has to start with a letter. We have right here a letter, okay? And then it has to have a digit, a letter. It starts with a letter, and then it has another letter or a digit, okay? And then an unlimited number of these identifiers, of these digits, okay? So if you're familiar with SQL, you're familiar with C, when you create like an identifier, it can't start with a number. You can't really call a table like 3 and then like, X. It has to be, you can call it X3, but if you call it a 3 and an X, then they put the number at the beginning, it doesn't work too well, okay? So effectively what we basically do is we define scanner rules so that it can take a string, a command, an SQL command, and it can break it up into pieces, what we call tokens, and effectively it splits it apart. So what happens here, it sees that it has an identifier, and then we actually go through and we try and say, is this token, is this identifier, is it a keyword? Keyword? We haven't used that term before. Keywords are things like what you see in green. Select from where. Okay, those are keywords in SQL. Same thing in C, the word for, the word while, those are keywords in the C language. And if you think of Perl and Python, there are keywords in those languages. And those words are special to that language. Okay? So what we're doing with an identifier when that string comes in is we're looking it up and we're saying, first, is the identifier too long? At which point we throw a warning, okay? And we also go and we, let's see, what does it do? It looks like it lower cases it for some reason, and then it actually looks it up and it says, is this a keyword? And if it's a keyword, we put a special like marker to it. If it's not a keyword, we just pass the text in. Okay. So the difference between a keyword and an identifier is the same reason. Have you ever tried to create a table called from? Like, so it would be select star from. It doesn't work because SQL considers that from identifier to be special, and therefore you can't call a table from. You can't call a table order. Like, you know how it says order by, select star, order by something. Last week, I tried to create a table called order, and because it was an order, like a sales order, and it doesn't work. You get an error, and you're like, well, what's the matter? It looks fine. It's because it's a special keyword. Okay. Similarly for numbers, here's a definition for an integer, and a decimal number, and a real number. Okay, and I get it gets a little complicated, uses a lot of regular expressions, but what it's trying to do, it's telling you that an integer is a string of digits, only numbers, only 0 to 9. Okay, because remember, an integer doesn't have a period, doesn't have a, it's just a number. Okay, so it would just be a bunch of digits. A decimal is a bunch of digits, but it can also have a decimal point. Okay, and then it has some more digits, or it has a digit and a decimal point and more digits, and then an exponent potentially, and then more digits after it. Right? So again, you have to break down how the number can be defined with like, is it an integer, is it a decimal, is it a real, meaning it's got like an exponent on the end. Okay, and these are different things to the database, right? And again, if it's an integer, we would use something like, we would actually call it a special type of constant. If it's a floating point out of range, we would actually call it a floating point. And if it's an integer that like will fit in the int field, we'll call it an iconst. And the same thing with the real and the decimal. We have different behaviors for those we would identify. Okay, so you can kind of see that this, I'm sorry I have to go backward, but this red number here, that's actually that's a separate type of token. It's a different type of token than everything else here. Okay, so the greens are the keywords, and the red is a number, in this case an integer, and the black are regular identifiers. Okay, so using the scanner, we've broken apart the SQL, and we've actually identified what type of tokens we have. Any questions about that? Yes, sir.
So what about truncating symbols, keywords?
Right.
Is it essential now, or it could be skipped because it's sometimes pain?
Right, so the question is, how do you handle the truncation of identifiers? Okay? And the reason for the truncation identifiers, and you can actually see the warning message right here. Okay? The reason for the truncation of identifiers is not because SQL can't handle them. It's because there are some internal data type, there are some system tables in Postgres which are defined to be very efficient and very fast, but they have a limited length. So the problem is that the current limit here for an identifier is 63 bytes. And anything that's longer than that, you're correct, it'll throw a warning and it will truncate the length of that. We could increase the length of the field, we could change it to one that's less efficient, but doesn't have a limitation of length. I'm not sure which direction we should go, but we do get complaints about that.
Well, this looks like problem with file system.
It feels like a problem with the file system. It's a problem with the system tables as we define them. And particularly, you don't see it so much in hand. When people are writing queries, they don't usually use long identifiers. But if you're using a program like some type of tool to write the SQL. A lot of times they'll create
Index names.
yeah, huge long identifiers and concatenate stuff together, and then you get, yeah. It's probably something we should look at, yeah. But that's exactly where that error is coming from, right there. But it's not the SQL, it's just the system tables. And we've always had that limitation. We probably should work on it. Other questions? Yeah, one of the things that when people ask questions, I have, after years, I realized I always should repeat the question because I know the nice lady's trying to get the microphone there, because if you don't have the microphone, like this side of the room cannot hear your question, honestly. So that microphone is really useful, particularly if the speaker doesn't repeat the question. I don't know how many times you've been at conferences that somebody asks a question over there, and the guy will go on for 5 minutes about the answer, and you have no idea what he's saying. Like, I'm like, wow, that sounds really interesting. I would love to know what the question was, to actually benefit from what he's saying. Yeah. So yeah, it is quite interesting. We're good. Okay. So here is like the proof, I would say, of what I'm talking about. What's happening here is that you're basically looking, this is the original query that I showed you, okay? But what has happened, it is broken up into tokens. And you can see that every single token now is on its own line. This is what we call lexer, or this is called lexing. There's a tool called Flex, F-L-E-X, Flex, that we use. And it's basically broken the string down into every little token. Even the white space is a token in this example. Okay? Even the white space, it's all split apart. And you can see kind of the line numbers at which point it's identifying. And then it gets to the end and it says it's done. But that's just the scanning part. Now we have to look at the parser. This is the second part, the parsing, which is done by Bison or Yak, depending on what you're using. And this is a very, very simple example of select. This is not the real example. This is all pared down. Okay? But what it's showing me is, do you remember I showed you the green before, the keyword when it comes across, it's special. So what it's done is it said, oh, I see the special keyword select, right? Here we go. I see the special keyword select. Let me put that here so I can remember what time it is. There we go. And then I see what we call an optional clause called distinct, and then another action called target list, and an into clause, and a from clause, and a where clause, and a group by clause, and a having clause. And these are all defined farther down in the file. So this is like a hierarchical thing, and you could look at each one of these. In fact, if you're curious, and you go into the Postgres source code, and you look at a file called gram.y, gram.y, this is the file. So I'm showing you a little piece of that file. And what it's saying is when it sees the keyword select, and it can then have a whole bunch of other optional clauses, and if all of this matches, then I want to create something called a select statement, and I'm going to assign all of these clause returns into that structure. So what I'm doing is I'm mapping an SQL command to an actual C structure. This is how that whole thing kind of works. It's basically saying $2 is distinct, so this is 1, 2, 3, 4, 5, 6, 7, 8. $2 is distinct, so that would be $2. $3 is the target list, it's that one. Here's $4, $5, $6, $7, $8. Okay, so it's basically assigning different clauses in. And this is part of the reason it's hard to make a pluggable parser, because you'd have to abstract out all of the mapping that's happening here. And that would be kind of hard. But effectively what happens is that select is coming in, it's just getting assigned straight across, and then once it's done that, it creates what's called a select statement, and then finally through the SQL it runs some more, and it creates something called a query. This is a select statement right here, and you can see it basically filling in all of these C structures here. Where's the distinct? Up here. Here's the distinct one. Here's the thing where you do a limit right there. For update is down here. Having a group by or where clause. Here's your from clause, your target list, and so forth. So it's taking the string, parsing, lexing it, parsing it, and then filling in those structures. And then we run some more. And but here you can kind of see it actually parsing and looking at all these examples. Now what happens if I type a mistake in here? What if I use a word and something doesn't match? What happens? Do you have any idea what that would be? If I make a mistake at this level, if I can't parse something, what does the user see? They see a syntax error. Yeah, that's exactly what a syntax error is. It means that we couldn't parse what you gave us. There's no rules matching the list of tokens that you supplied to us. So I think if I type like select, like I'll just get a syntax error, because it'd be like, well, there's a keyword select, I understand that part, but then select, that doesn't make any sense, and it just throws an error. Okay, so that's the point at which you get syntax errors. Way early here in the processing, that's when you get the syntax error. Okay. And you can actually see this is a little kind of mixed together of the scanner and the parser. So you can see it here. It finds the select token, and then there's the select rule, and here it finds the first name, and it's an identifier, and it actually assigns. It checks distinct, no it's not distinct, and it goes down, and I said, okay, that's identifier, and then the word from, and then that's an identifier, and it's a keyword, and it kind of walks through that kind of code, and it finally gets to, where is it? Hold on, I want to show you, here, this. It finally gets to this, and this is what we call query structure. And this could represent an insert, an update, or a delete, or a select. Okay? And this is kind of the main structure for everything that's going to go to the optimizer and down to the executor. They're all going to be using the same structure. Okay? So basically you have a type up here at the top, then the command type. Is this a select, an insert, an update, a delete, or some utility command? So that's tells me what's happening here. It's called the command type. And then you have a whole bunch of other stuff. Group by, limit, joins, range table, aggregates, portals, temporary, binary. This is all the stuff about the SQL you sent us. This is what I'm giving you.
What is portal?
What's a portal? A portal is when you are running so the question is, what's a portal? So you're running the query, but you don't want the query to be, you don't want the results to go back to the user. You want to store them temporarily somewhere. So like a cursor, okay? If you create a cursor, you're creating a portal. Because you're going to run the SQL, and you're going to kind of hold the results. And that's what, and there's a bunch of other cases we use portals, but that's the kind of most common one, where you're kind of saying, don't send it back to the user, just kind of keep it here, and we'll work on it later. If there's no portal, then it gets sent back right away. Okay. Now you might be like, well, okay, how do we do the from clause? How do we do the list of columns that you want? And I'm going to back up here. Effectively, one of the things that you see in the code all over the place is the concept of a list. And I'm not sure how many of you have used like Lisp before, the language called Lisp. But it's basically kind of a list-oriented kind of a language. And for example, if you say select, column 1, comma, column 2, column 3, column 4, column 5, you're creating a list, right? Or if you say select from table 1, table 2, table 3, table 4, select from customer, order, part, office, department, you're creating a list. And Postgres has the ability to record those lists in the system. It uses some commands very similar to Lisp and some kind of functions that help us to manipulate it. So for example, the from clause is a list. So it's basically an entry called a range table. This is a single table that you're using. Like for example, you know how you use alias? Like you can alias a table with as, right? So that's actually where we record the alias. If you're using inheritance, we record it here. The name of the table is recorded here. If you're using a subquery in your from clause, we record it here. So you kind of get the idea and then you make lists of these, okay? Same thing with a column. Like if you select, column 1, column 2, column 3, column 4, those are called variables. I don't know why they're called variables, that's what they are. They're probably from the relational algebra days. So if you actually have a number or it's a constant and we actually have a whole bunch of information we track, same thing with the return values. Let's see, vars are references to columns in your where clause usually. That's usually what a var. So if in this case, let me go back to my query again. This would be a var right here. So this is a var. This is a range table. And this is a target entry. Okay? This is a var because it's a column in a table. Okay? This is a range table because this is a table, it's a range of values. And then this is a target because it's a return. So it's a target for a return, is how we would express it. And we have C structures for all of those. So where is it? This is the range table, that's the var var, and that's the target entry. Okay. Then you put them all together in this query structure. You can see target list right here. That's your target list. That's what you're returning. If you selected 3 columns, there's going to be 3 entries in that list right there. Okay. Let's see. Here's your range table. This is your from clause right here. So it's a list. And we have a list of all of the tables involved in that particular query. And even your where clause is here. Where is it? Where is my where clause? Distinct clause, limit clause. Why am I not seeing it?
Should be join tree, probably.
Join tree.
Yeah.
Oh, right up here. I'm sorry. Yeah. In fact, I should have. Yeah, it says from expression right here. So it's the join tree. I was looking for a list, but it's actually a from expression, and that's your list of tables you're pulling from. Okay, and so that's really all the parsing is trying to get you to this point where you have a query structure that you can pass farther down. Any questions?
Where is this structure located in the sources?
Where is this structure located in the source tree? The query structure, the name of the include is, I think it's source include parser. There's a bunch of H files in there, and the query structure would be in there. I don't remember the name of the H file, but it would be a query with a capital Q.
Parse nodes.
Oh, parse nodes. Thank you. That makes sense. Parse nodes, right? I wasn't sure if that was a part. I guess it is. Yeah. Thank you. I knew that all of the other ones, like the var and the range table, those are all parse nodes. I didn't know that the query was also parse. Good to know. This is what it looks like, and I don't expect you to read this, but this is kind of the output pretty printed of this thing. So this is an example of a query node, and you can see like key value, key value, key value. Here's a range table. This starts to now make sense. We saw this earlier. Remember this? We saw this with that big thing that scrolled all around the screen. We're like, what is that, right? I mean, we saw it here, right? Oh, right there, right? And in fact, if you take a look, there it is, query right there. And there's all of the key values going all the way around. And this is what it looks like, right? Here's our query, key value, and you can see here's our range table. Here's the table that we're referencing called friend. And here's all the columns of the table friend, okay? And we have no, it's not a temp query, table query, there's no portal, it's not binary. You can kind of get an idea of what's going on. Now it makes sense a little bit, a little more sense, okay? Because you kind of walk through how we create this thing. And that's the same output, exactly the same. Here's the join tree. We're not doing any joins, so we don't have a join tree, but we do have a range table here. Okay. So yeah, that's the interesting part. That the join tree is actually the part of the where clause. Other questions? So let's get to the optimizer. So everyone's good with the parser? Okay, good. So the next step is the optimizer. I'm scripting the rewriter. It's used for views and rules, but I'm not going to go into it. It's not that interesting. But the optimizer is interesting, and this is again one of the parts that always interested me as an application developer was how does the optimizer work? How does it know all these amazing things? How many of you have ever seen how many of you have ever run explain or looked at the optimizer output? Is that something a lot of people do? Okay. Yeah, and sometimes it's very cryptic, very hard to understand. When I used to do it with Informix and Ingress, it used to create this huge, very complicated banner of arrows, and I could never understand. Yeah, it was just mysterious to me. So Postgres is not mysterious, obviously, because we have the source code and we can understand it, but it is interesting. The optimizer has to be pretty smart about what it's doing, okay? Because it has to make three primary decisions. The first decision is how do I get the data? That's typically related to how do I do a sequential scan, do I do an index scan, or do I do a bitmap index scan? Those are my three choices the optimizer has to make. And then once it makes those choices, it then has to figure out how do I do the joins, and what order do I do the joins in. So there's a whole bunch of things that it does that makes your life easier as a programmer, because you don't have to think of them. You don't have to figure out, oh, do I use an index or not, or do I use hash join or merge join. The optimizer automatically figures these things out for you, and I think that's one of the real powers of SQL. One of the problems of no SQL is it doesn't have an optimizer in most cases. And without an optimizer, it's hard to kind of bring data together. It's hard to, you have to do a lot of work in your application. So you kind of, with the optimizer, you just give it a very complex query, and it's like, okay, I'll find out how to do it. So, what decisions does it have to make? The first decision it has to make sequential scan. How do I get at my data? One way of getting at your data is just to read the whole table from the beginning to the end, right? And this works really well if you want to see most of the data in the table. But if you only want to see some of the data in the table, you'd probably use an index, because the index allows you to kind of go only to the specific row that you're interested in instead of the whole thing. Okay. And then also we have something called a bitmap index scan, which allows you to kind of break up the it's kind of a combination between a sequential scan and index scan. It allows you to take a couple indexes and create a bitmap, and then the bitmap allows you to look up the matches really quickly. So this is great if you're going at all the data in your table. Okay. This is great if you're looking at only a few rows from your table. Okay. And this one is good if you're looking at like some of the rows, but not all of the rows. Or let's say, 5% or 10% of your rows. It's kind of like in the middle is the bitmap scan. And I'm going to show you a slide later that gives you a better illustration of that. But right now, we'll just kind of stay at that point. Okay. The second thing it has to do is something related to join methods. How do you want to bring your data together? And we actually have 4 methods of doing joins. Okay? The first one is called a nested loop with a sequential scan. I'm going to show you a diagram of that. The second one is a nested loop with an index scan. Third one is a hash join, and the fourth one is a merge join. And the optimizer has to figure that out. Okay? Here's a illustration of a nested loop. It's basically compare every row to every other row. Completely inefficient. You're just matching everything to everything else. Very slow. However, it's very good for small tables because you've got like 5 rows in 2 tables. You want to join them together. This is like, 25 comparisons, you're done. There's no setup, it's just very easy, just compare. Okay. The second one is an index, nested loop with an index lookup. This requires an index on this side, but it allows you to do very quick lookups. So you can say, okay, is there an AG? Oh, I don't have to look at the whole table, I can just use the index, and it points me right at the matches right here. Okay, so there's an example where an index helps the optimizer. It says, oh, you have an index there, then I can basically join this table, this other table using this index, and I get the result very quickly because I can use the index. I don't have to compare it against every other row in the table. So obviously the index makes things much quicker. And I'm going to show you, after our coffee break, I'll show you some examples of some queries that actually use these methods, and you can kind of see a little more graphically what's going on. Okay. This is a hash join. A hash join means that I have taken the whole one of my tables and I've created a hash. And then I've compared, and then now once I've created the hash, I can look up matches very quickly. I can say, okay, is there an AAY? Okay, I'm just going to hash. If there's a match, it's got to be only here in this set of this bucket. We call it buckets. Okay. Is there an AAG? No, there isn't. Is there an A? Oh, it's over here. Okay. So what the hash allows me to do is to quickly route to potential matches without having to go through this kind of business. Okay. But the bad side is I have to hash. I have to do the hash operation. I have to hash the whole table, and I have to store it in memory, hopefully. Okay, so that's an expensive operation. It doesn't mean it's going to take longer than this. This is just terrible. If you had 1 million rows on both tables, this would take what, 1 trillion comparisons? That's bad. Right? 1 million times 1 million would be 1 trillion. That's like never going to finish, right? So again, you can see why nested loop is really good just for small tables. But if this was 1 million and it wasn't and it fit in memory, then you can do lookups real quickly on it because you get your answers right away. And this one, this is really for really big tables. Here you're actually sorting both sides. It's called a merge join. And in a merge join, you basically sort this side and you sort this side, and then you can walk through and make comparisons because they're all in order. So, is this a match? Yes. Is this a match? No. Okay, so now I'm going to go to the next row, but I don't have to start back at the beginning. I can start where I stopped because they're in order. Right? That's a match, that's a match, that's not a match. Okay, so now I can go down here, and I don't have to start at the beginning, I can start again where I stopped. So I'm now walking through the two tables in a synchronized way. And this is very fast, although I have to sort both sides, so that can be expensive. Yes, sir?
Excuse me, does it use any kind of binary search on the inner side, or just starts from the last found value?
Okay, so the question is, are you doing any kind of binary search on the inner side? Because now that it's ordered, we could kind of do a binary search to find the matches I need, right? But the reason I don't do that is because I've sorted both sides, I kind of know that if there's, well, how do I explain it? So, if I was to pick a random row over here, random, then I would do a binary search to find it. But because we're doing a join, we know that we have to walk through every one of these, and we know we have to walk through this. So effectively, we don't even need to do a search. We know that either the row is at our current location on the inner side, or it doesn't exist.
But there can be huge gaps between rows.
So the point is there can be huge gaps between the row, and that's correct. So let's look at an example here. So this matches to this matches to this, right? This matches to this, so that's fine. This matches to this, okay? Now let's keep going. So this doesn't match to here, right? So now I'm going to say, does this match to here? And it doesn't. So I'm going to stay there. I'm going to stay in that location. And I'm just going to keep going down until I get a match. So even though I may have 100 rows here at which there's no match here, that's okay. I'm just going to keep going. But perhaps, let's suppose it's A, B, A, C, and let's suppose I have 100 AADs. 100 of these. Okay. So I'm just going to go, is this AAD match AAD? No. And I'm just going to keep no, 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 no. And I'm just going to keep going back there because I know there can't be anything, unless I get to an AE here, I'm never going to match that thing. So then if I get to an AAG, okay, then I'm going to compare, I'm going to say, no, it doesn't match, but it's also bigger than that. That's the point I didn't get into. So as soon as the match is bigger than this, then I'm going to start going down, I'm going to start advancing this way until I get to something that's equal or bigger than the one I currently have. So I can skip this way, and I can skip this way. And it's actually more efficient than doing a binary search because we kind of know that either the value's there at the one we're pointing to, or it isn't. We just can just keep going. So my point is that if this was AAD and then all the way down to AAG, we would say no, 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 no. And we got to AAG, we'd say, okay, it's not a match, but also this is lower. So I now need to keep going here, 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 until I get to an AAG or something bigger than AAG. And then I can stop and I can keep going farther that side. So I've simplified this quite a bit. But that's why I'm saying you kind of walk the two sides in lockstep. You're kind of advancing down the outer side, but also you're advancing down the inner side because if the inner side is less than the outer side, like the AAG example, then I can move down. I can move down on the inner side without even advancing on the outer side. Right? It's not really like a case like this where I'm locked into kind of doing that. You're kind of walking as you go. And this is very, all these are very time tested. All of these join methods are present in pretty much every relational database. These are very standard ways of performing joins. Yes, sir?
Is there any some advice to sort with another reverse order? Does it can help if you know the data?
So the question is there a value to sorting in some kind of reverse direction? It's hard to say. You can, it depends, and when I have some slides later that I'm going to kind of show this, but the way it works in this example is we're doing an ascending sort, right? And of course, the two sides, I believe, have to have the same ascending, descending, matching ordering. Now, you can create indexes that are descending order, but they're only really useful in cases where you have a multi-column index, and you want to do descending like in the middle. Like for example, if you want to say column 1 ascending, column 2 descending, column 3 ascending, and you have a where clause or an order by that matches that. That's when it's useful to say ascending and descending. But usually in this type of case, there's not a lot of value to change in the order of the sort because it doesn't really buy you anything in terms of how the process works. But I do think you can, in fact, Theodore might know this answer. Whether we can do a merge join backward, like from the back forward, I think we can. We can do a, Theodore, can we do a merge join from the bottom up? From the end? I think we can.
Yes, we can, but we cannot use join except for equality.
Okay, so that's the question. So the answer is you can do it you can do a merge join from the bottom up, from the end going to the beginning, but he said you can only use it for equality. Only equality joins, which is probably 99% of what you're going to do. But what he's also saying is you can do non-equality merge joins, which sounds really scary, but it works. So you can say column greater than another column. And you can also do that as a merge join. The reason I know we can do it is because we had a couple bugs in how we did it. You remember, this was a couple years ago, but I remember somebody said this merge join doesn't work when you do it this other way. And I believe it was for the non-equality particularly. Long fixed, but I remember having a bug related to that. So that's a good question. The idea of doing it in reverse order is something, yeah, that is possible. Yeah. Yes, sir.
Could merge join use indexes, some indexes? So
could merge join use indexes? Absolutely. I'm going to show you an example later where we have a merge join that actually does use indexes. So what happens in that case is you do not have to sort both sides. You actually can do the merge join through the index, which is, you're basically walking the index on both sides. And so this is another example. A lot of people think of indexes only for comparisons. Like, if we think of our earlier query, customer ID equals 12, right? They want to put an index on customer ID. What they often don't realize is that indexes are very useful for joins as well. And that's something people don't really think of. They're normally thinking of indexes for things like equality comparisons, but not necessarily for joins, but particularly for merge join and for this nested loop index scan. Both cases an index is helpful. And that throws, a lot of people don't realize that. They're always thinking of looking up primary keys, for example, single row lookups, but indexes are also useful for joins. Other questions? Yes, sir.
Can index be used for filtering? Index contains some data, and in fact, we calculate some function and store it in the index, right? Can we use the data to filter the values that comes out of query.
So the question is, can you use an index to filter the values that come out of a query? And the answer is yes, although there are actually 3 ways of doing it, okay? So the first way that you kind of alluded to was the idea of creating an expression index, of storing a function output or some kind of calculation inside an index. That's something that we've always been able to do. You can say, you know, create an index on the factorial of this column, right? I don't know why you want to do that, but you can. So that would be the first way, right? The second way would be that you have an index and you have some kind of limit clause, and you say, give me the 3 highest values in this column. Okay, we can walk the index and find those 3 top values by going to the top of the index, you know, and then going backward and finding the highest matches, and then only running those highest ones through the query. So if you use a query and a limit clause, we can use the index to kind of pull off the top or the bottom entries from the index, and then just run the query for those rows rather than running it for the whole thing and then sorting it in that whole business. And then the third way, I guess you would, let's see, the third way, I forgot the third way. The third way of filtering on an index, let's see, there's limit, expression indexes, and limit. Maybe there's only 2. Does that answer your question, or was there another question?
Yes, partially actually.
Yeah.
The very first way that seems not to work actually.
Yeah.
So it does work if you apply some equal comparison, for instance, but it doesn't work when you try to filter based on that value. For instance, you create an upper value index, and you try to filter values using like condition with no prefix. So you supply something like upper colon, like %, your value here. It doesn't seem to use index for that particular case.
Okay.
Is there any like inherited problem, or can it be fixed? What is your vision?
Okay, I see what you're saying. So let me give you the third one that I haven't talked about yet. The third one that I threw out of my head is the idea of pulling data directly off the index, what we call an index-only scan. So we have the ability of pulling, not even going at the raw data, but pulling, if you run a query that only returns indexed columns, we can pull the rows right off the index. Okay, but that wasn't your question. Your question was, you create an expression index on the uppercase of a column, and then you go and you do a query that does not an upper of the column, but does an upper of the column with some type of regular expression or some type of like comparison. And you're saying the index isn't used in that case. And the reason it's not used is because the expression indexes only become active when the where clause exactly matches an equality for a value. So what you're doing is you're doing a function call, but instead of an equality, you're using a regular expression, a tilde operator or a like operator, and then some pattern. And the system just doesn't know. It doesn't know how to use that index properly. It's probably something we should improve. But we do get that question quite a bit, that there's no way to create an expression. The expression index was kind of special because you're mixing the idea of, in your example, the reason it doesn't work is because you're mixing the idea of a pattern with an expression index, and the system isn't smart enough to realize that it can use that. So it's something we do get complaints about. I haven't heard how to fix it yet, but it's something missing, I think. And maybe when Magnus comes back, I'll ask him if he has any ideas on that. Well, you know, actually during the break, I'll see if I can get an answer for you. How's that? Because we have a break in 4 minutes or so. And I'll see if I can get an answer. Because that's a very common question. Everyone heard the question? I think the idea of creating an upper index and then trying to do a regular expression on it, like a percent sign at the end, so wild card it. Yeah, it's a little tricky. Other questions? Okay. Effectively, let's just try and wrap up the optimizer. So the way the optimizer works, in fact, we're not probably going to wrap it up in time, but let's get a little farther. So the way the optimizer works is it creates something called a path structure. And a path structure is basically a definition of one way of getting at the data. And I know that's really vague, but it basically has a way of getting at the data and then a cost associated with it. So what the optimizer effectively does when it runs a query is it just says, how many ways can I get at the data? Can I do a merge join? Can I do a hash join? Can I do an index lookup? Can I do a bitmap index? Can I do a sequential scan? And it generates a whole bunch of ways of running your query. And then at the end, it just says which one is the least expensive, and it picks that one. So that's all it does. It says, it takes all the things we talked about, all these sequential scan, index scan, bitmap scan, hash join, merge join, nested loop, and it just tries them all. It doesn't try them all, it gets costs for every one of them. Okay? And then once it gets costs for all of them, it puts each option in something called a path, and then it picks the one that's cheapest, and that's what it ends up running. All right? So this is an example of what we call one of the internal structures for the optimizer. There's a whole bunch of them. There's path key item, there's rel op info, and you can kind of see like some of the stats in here, like how many pages does it think it's going to touch? Yeah.
Does it mean opt, the name? Optimal or optional?
It stands for just optimizer. Yeah, OPT in that case is just optimizer. It's not optional or optimal. I think it's just the optimizer part, because this optimizer is like one of the earlier areas I kind of got into, and it was just riddled with problems. I remember, and I'll probably finish here, but I remember back in, I guess, '97, we had inherited this optimizer from Berkeley, and it was originally not written in C. It was originally written in Lisp and then converted to C. Yeah, and we were getting these reports that the optimizer was taking just forever to figure things out. Like it would take like 5 minutes to plan a query, and we're like, what is going on, right? And the reason it was happening is because, as I told you before, the optimizer just has a tendency to try everything. So it was trying everything. If you had, if you mentioned 5 tables in your query, it would, well, let's see, 5 tables, you can join those, what is that, 5 times 4 times 3 times 2, what is that? You can join it 120 different ways, okay, 5 tables, 5 factorials, 120. But then you have to do, you have an optional merge join and a hash join and a sequential scan and an index scan and a nested loop with an index scan and a hash join, right? So all of a sudden you had thousands of possibilities that these things were doing, and it would just cost all of them. Every time you ran a query, it would just try everything, and it would take forever to finish. So I'm a little too intimately aware of these structures than I'd like to be, but one of the early things that Tom Lane did, and he's obviously sort of one of our bigger optimizer guys, is to kind of understand what it was doing and start to trim down a lot of the stuff it's doing. And I'm going to go into that as soon as we come back from our coffee break, and hopefully a tea break too, because we're in Russia, right? So when we, but sort of paring down a lot of the stuff that it does and tracking and stuff, because if the optimizer is not fast, it's useless. Like if optimizer is there to make things faster, if it's making things slower, then something is obviously wrong. So let's take a break now for half an hour. We're going to have some drinks, and then when we come back, we'll go cover this.